for the first page?
Not yet. This is just the notes part. So we have bisectors, and if you remember, a bisector cuts things in half. So like if you bisect an angle, you get two equal-sized angles. If you bisect a line segment, you get two equal-sized pieces. So it cuts things in half. So a perpendicular bisector is a bisector, but it intersects at a 90-degree angle. So it's perpendicular. So if we have a normal bisector, just a regular old bisector, so if I have this line segment here and I want to bisect it, we think this is about a halfway point. We'll just say that's halfway point. I can come in at any angle and I can bisect it. And it's just a regular old bisector, it's not special. If I have another line segment, and let's say, we'll just say that's about halfway. To be a perpendicular bisector, I have to come in at exactly a 90-degree angle. Oops. Okay, so we're still bisecting, it's special because it's at a 90-degree angle. We have two theorems related to perpendicular bisectors. The first one is the perpendicular bisector theorem, which tells me that if a point is on a perpendicular bisector, so if a point is on a perpendicular bisector of a segment, oops, distance has an I in it. Yes, then it is equidistant from the endpoints of the segment. Okay, so how this will work out, better line. If I have this segment, AB, let's say, A and B are the endpoints, and I come in with a perpendicular bisector, and I bisect it, and I find any point on that perpendicular bisector, so C, then that's going to tell me that the distance between C and A and the distance between C and B are the same length. Okay. And it kind of, makes a triangle. And if we have a triangle with these two are the same length, it's an isosceles triangle, so that tells us a few more things, right? Now, the converse of the perpendicular bisector theorem, so remember a converse turns around and goes backwards, flips it around, is that if you have a point and it's equidistance, equals E. I can't spell. Okay, so this one is telling me I have a line segment. We'll just call it YZ. If I have some random point in space, and it can be anywhere, it can be down here, it can be up here, it could be right here on the segment itself. So anywhere along the line as long as it's equally distant from the 2 points. So I could put it right here and call it x. Let me write that off to the side. And if this distance is the same as this distance, so this one is the same as this one, then that means that x is on the perpendicular bisector. So then if I draw a line through x that's perpendicular to yz, it's the bisector. So I will do purple or hot pink?
Purple.
So I come in and I draw a line through x that goes through yz. It will end up being perpendicular. And it will end up being a bisector. So you can go either way. You can either have the segment and have the perpendicular bisector and the point becomes equidistant, or you can have the segment and have the point that's equidistant and use that to find the perpendicular bisector. Kind of just a little bonusy, perky thing. Once you find this point where it intersects, you've found the midpoint, because the perpendicular bisector hits at the midpoint. So that's another little thing that you get from this. You can use the fact that we have the perpendicular bisector theorem. No, to find different measures. So if I have a triangle, well, not a triangle, but it becomes a triangle, and I find that C is the perpendicular bisector. It's perpendicular C and it's bisecting, and A is on that line right here, then I know that this distance and this distance are the same. So if this one's 4.1, this one is 4.1. Okay, here I have these two distances are the same, and this is perpendicular, so that tells me it's a bisector. So this distance and this distance will be the same. So if this is 3, this one is 3. And then I can use the same thing with some algebra. This is perpendicular, these are the same length. That tells me that these two are the same, so I can set those equal to each other. Whoops. If I write down the correct numbers. Okay. I can subtract 2x from both sides, and I get 3 is equal to 2x minus 7. Add 7 to both sides. 10 is equal to 2x, so x is equal to 5. Why did I write down RT? I typed that wrong, that should have been RS. Okay, so if x is 5, we can find RS, we plug the 5 in. So I get 20 minus 7, so 13. That's not a 5, that's an S. Does that make sense? Okay, so finding these two lengths are the same. That means these two lengths are the same. Okay, so I can plug in, set them equal to each other and solve for x. So subtract that 3x from both sides. And if you need markers and stuff to label again, I have that box of markers up here if you need the color, if it helps. Thank you. So 2x minus 17 is equal to 1. Add 17 to both sides. 2x equals 18. Divide by 2, and x equals 9. But we're not done because it said to find FG, not x, right? Mm-hmm. So find each measure, and then it tells me FG. FG is this length right here. Yeah. So I'm going to plug in that 9. 5 times 9 minus 17, which is going to be 45 minus 17, which is going to be 28. So here's my final answer, is 28. Bless you. And if this one's 28, this one is also 28.
Oh, no.
I'm going to go ahead. This length is the same as this length, and this length will be the same as this length. If this was not a made-up triangle, like with algebra to be made up, this is an impossible triangle. This is a right triangle, right? This part?
Mm.
The leg of a right triangle cannot be longer than the hypotenuse.
Okay, so the line.
This is a correct answer. We did the math correct, but when they made the algebra on this page, they weren't being realistic. Because there's no way that you can have the leg of a right triangle to be longer than the hypotenuse of the triangle. The hypotenuse is the longest side.
Okay, so it should suppose it's.
Yeah. So, but I mean, I wanted you to be aware of this because some of you might see something like this and know that this has to be shorter, that the yellow has to be shorter than the green. I think you did it wrong. But when people are making up problems, they don't always make them, you know, for stuff like this where they're coming up with algebra, they don't always make it realistic to the triangle. So don't automatically assume you're wrong. But if you see something like this and you go 28, that can't be 28 because that's 13. Just go back and look through your math again and just make sure you did it right. But that, which is what I did. I went through and I went, nope, that's right. Yep, nope, it's 9, and 9 times 5 is 45, and yep, that's right. So the algebra was not correct to the geometry as far as realistic proportions of a triangle. But we did the algebra correct, so this is the right answer. Does that make sense?
Mm.
So something. Okay, KL, we want to find this length right here.
So KR is 4.2, then KL
Has to be 4.2, exactly. So that one was pretty simple. We just had to make them match. And then TU and UR, again, these two lengths are going to be the same because these two lengths are the same. So I'll set those two equal to each other and solve it. So take 2x from both sides. You get 3x minus 30 is equal to 24. I subtracted the 2x from both sides, right?
Oh, I wrote it the wrong way.
That's okay. You'd get 24 is equal to 3x minus 30. Not the wrong way, just the other way. Oops, that's a plus 30 on both sides, not a minus 30. So add 30 to both sides and I get 3x is equal to 54. Divide by 3. And you get x is equal to 18. Okay, but I want to find TU, so I need to plug that 18 in here. I don't know what's going on with my pen. Okay, so 2 times 18 is 36, plus 24 is 60. So this length would be 60, which would make this length also 60. Which can be realistic because I have no idea what this length is. It could be, you know, 100 for all I know. Okay, so if you have two lines that intersect, those are just called intersecting lines. But if you have 3 or more lines that intersect, when they intersect all in the same point, it's called concurrent lines. So if, when you draw, when you draw like that X with a star thing, these are all concurrent lines because they all intersect at this same point. So it has to be 3 or more to be concurrent. The point where the lines intersect is called the point of concurrency. It sounds like money, right? Because currency is part of money, but it's the point of concurrency. Now, in a triangle, every triangle has 3 sides, which means it has 3 perpendicular bisectors, and the perpendicular bisectors are always going to be concurrent. And that point where they meet, the point of concurrency, is called the circumcenter of the triangle. So if we look at this picture here, if these are the perpendicular bisectors, then P would be the circumcenter. So let me mark that these are all bisecting. If I have another triangle, let's say I have a triangle that's not quite isosceles. It's just called the circumcenter, and it's not always in the center.
Oh.
It's called a circumcenter, but it's not necessarily in the center. So if I do this bisecting here, perpendicular, it's not actually going through the vertex, but I can't draw it very well. And then, so this one's the perpendicular bisector here, and let's just say that's perpendicular there. So this is, you can see it's not in the center of the triangle. It can be anywhere. It's called a circumcenter, but that doesn't mean it's in the center, and that's confusing. As a matter of fact, the only time it's in the center is if you have an equilateral triangle. Otherwise, it's not in the exact center of the triangle. It's going to be off. Does that make sense? However, we have a circumcenter theorem, which tells us that the perpendicular bisectors of a triangle intersect at a point called the circumcenter. Now, if you were in the center of the triangle, you would be equidistant from the sides. The circumcenter is equidistant from the vertices. So what that means is if we look at our triangle here, this length, and this length will be the same. These lengths, PD, PE, and PF, will not necessarily be the same unless you're an equilateral triangle. So the center of the triangle will be equidistant from the sides. The circumcenter is equally distant from the vertices. So look at a circumcenter. The circumcenter can be on the interior, exterior, or side of a triangle. If you have an acute triangle, it'll be inside the triangle. If you have an obtuse triangle, it's outside. And if you have a right triangle, it's on the side. And actually, it will be on the hypotenuse.
I don't get what you said inside, outside.
See how this point is inside the triangle?
Oh,
Here it's outside the triangle, and here it's on the side of the triangle. And each of these is a perpendicular bisector. So even though I may not have drawn them properly, so I'm bisecting each side with a perpendicular line. And the reason we get the obtuse triangle, this meeting outside, is because if I hit this side perpendicularly, I'm not going anywhere near the vertices, right? I'm going straight up. And if I hit this long side perpendicularly, see how it has to meet outside. And here you can see that it would have to meet inside, because the triangle is kind of more closed. And then with the right triangle, it ends up hitting on the hypotenuse.
Is that also the midpoint of the right triangle?
On the midpoint, yes, it would. Well, it would be the midpoint of the hypotenuse. Yeah. So on the right triangle, you get the midpoint of the hypotenuse is also the circumcenter. So this would be a midpoint and a circumcenter.
Wherever the red dot is, or it has to be on the line?
It's on the line. It's hard to draw.
I got you.
Yeah. So on the page, the 5-1 skills practice, if you skip to 7, 8, and 9. Okay. So if we look at this, and I asked for BR, let's label this triangle. Okay, these are perpendicular bisectors. That means that this length is the same as this. This length is the same as this one. This length is the same as this one. And then our circumcenter means that these lengths, 2, 3, 4, are the same as each other. Okay, so that's our labeling.
Those three
Don't forget
are the
forward
same.
right there, too.
Which one? These?
Huh?
Which one?
Oh. But you don't put telemarks on the other one? On the other.
These ones?
Yeah, right there.
No, because this one is to a side, and the circumcenter is not equally distant to the sides. It's only equally distant to the corners. So I don't know anything about these lengths.
Does it matter like where you put the 1, 2,
No.
3?
No, I'm just showing, all that does is show which ones are the same size.
Okay.
So it doesn't matter, like the one could be on the longest or the shortest, or that part's not important. We just know that these two are going to be the same length, these two, and these two, because these are perpendicular bisectors. And since they meet at the circumcenter, that tells me that the lengths to the corners are going to be the same. Once I have that, I can say, okay, what's the same length as BR? RA. And what's the same length as CS? Same. And the same length as BP? Well, there's two of them. I could do AP or CP.
So, what is P? Like, P, like...
P is the point in the center.
P is the point?
Yeah, P is that point right here where they're all meeting. This is P.
What TC we can run to BR
TP?
No
TC.
No.
No, TC. Well, oh, sorry, this P is confusing. I meant to erase that out. That shouldn't be on there because that's for the next picture down.
So it's T, right?
Yeah, this is T. So BT and BR, I don't know for sure. If it turns out that this is an isosceles triangle, yes. But since I wasn't told it was an isosceles triangle, I can't say for sure that it is, even though it looks like it is to me. But because we don't have anything that tells us for sure, then I can't assume that. Does that make sense?
So my question is, okay, you like B,
BP? Uh-huh.
No, okay, forget it, I got it now.
You sure?